Right, our next speaker is Dr. Kenji Takeda, who I've known for quite a long time, but he's an active promoter of e-science, big data, artificial intelligence, and currently is very active in Microsoft research in terms of the Azure for Research cloud, and I'm sure you're going to give us a riveting talk.
Oh, I hope so. Thank you, Peter, and delighted to be here. One thing that we believe in really at Microsoft is this phrase, let researchers be researchers. Okay, so let the people who are good at what they're supposed to do and what they're trained to do their job, and for researchers, that is researchers. For developers, that's developers, and for sysadmins and IT pros, let's make sure we've got the systems in place for everyone. And we see that the world today really looks something like this. We have the things like Supermove, which are absolutely incredible. We have university clusters, and then we have the majority of users, I would say, who have a laptop or a desktop. And we have a time now where reproducibility is either hard or impossible. And particularly in pharma, we know that we're in crisis around that. And so we believe a shift where the cloud can help, and we still believe very much in exascale supercomputing. There are some things where we need things like Supermove to be able to do those calculations. We learn from those experts. But we can also deploy clouds where we can integrate some of the results from the exascale supercomputers with people doing things on their laptops and share our methods, so that we move into a world of open science where reproducibility is the default. That's what our PhD students should be taught, is not just how to log into the email system, how to do a literature review. They should be taught when they come in and start their PhD that their work must be reproducible, and that's really how we need to change science. And cloud can play a really nice role within that. And one of the things we've talked about really is you only use technology that you trust. And it's not just about compliance. It's about the security, the privacy, and the transparency of what's happening in the cloud. And it's the one thing we pride ourselves at Microsoft, because we've been doing this for a very long time. And particularly where we deploy data centers in region, where we have multiple data centers in the UK. And the reason for that is we've had long conversations with people like the NHS, the government. We've worked with the European Commission over many years. We now have GPDR. How many of you are GPDR compliant today with your systems? Okay, you've got 12 months. Kicks in next year, this time next year, okay? We have that now in our cloud, okay? It's very, very important. And in the UK, where we've deployed data centers, we've worked with people who know how important that is. The Ministry of Defence is moving their workloads to our cloud. The National Health Service is moving to our cloud for some of their key infrastructure services. Okay, that is the level of compliance and trust that the Microsoft Cloud has. And we're in lots of regions, we like to say. We're in as many regions as Amazon and Google put together. But it does depend how you define regions. The one thing I would say is we are now investing $3 billion in Europe. Okay, think about that in terms of in our infrastructure. Okay, so the cloud vendors like us and our friends, we really do things at scale. And you can take advantage of that. And when we think about cloud, we think about CPUs. Okay, and we have that all over the place. When we think about, particularly for us at Microsoft, where we're really sort of leading the charge around artificial intelligence, some of these frameworks are really driving deployment of GPUs. And what's interesting, of course, is that people in biomed can take advantage of that. And actually, when I did my PhD in fluid dynamics, we did a lot of the early work around GPUs for CFD. But the thing is that Moore's law's ending, and so we need to look beyond GPUs actually. And I'll talk a bit towards the end about the future of what the future looks like beyond Moore's law and what we're doing with FPGAs across the cloud. And this is my eye chart, similar to others. And I think what I'd like to stress is we often think of cloud at this bottom layer of infrastructure and virtual machines, and that's not really where you get the advantage. The advantage you get is when you move to some of these higher level services that I'm going to be focusing on today, including serverless computing, so using Azure functions to do serverless computing, where we've seen before that can really transform how you think about your research. And we've seen a lot of talk around HPC in the cloud. We've seen a lot of talk about HPC. We've seen a lot of talk about cloud. And when I did my PhD, what's the definition of HPC? I think definition of HPC is at least an order of magnitude more than you can do on your desktop. Okay? And you can do that in the cloud. Real HPC, I'm a little bit of a purist, I can be, I would say is low latency. Okay? There's a key thing around high performance computing, high capability computing versus high throughput computing. And with real HPC, you must have an interconnect that can do low latency. Okay? And that's what we have in our supercomputer centers when we go to things like InfiniBand. And people have said that's impossible to do in the cloud. And that has been true, but it's not true anymore. So this is a Formula One CFD case running Fluent, and this is what I used to do before I left the University of Southampton and moved to Microsoft. It's 1,000 cores with over 90% efficiency on a real test case. This is the sort of thing a Formula One team was doing about 3 or 4 years ago routinely. Okay, Ferrari used this code to design their car for Sebastian Vettel. Okay, but the key thing here is the 2.5 microsecond latency. And how do you do that? You deploy real HPC hardware. What I mean by real, I mean InfiniBand, okay, and I mean demonstrable performance. There was this interesting paper, and there was quite a lot of discussion around this paper when it was published, which was a third-party benchmark, an independent benchmark looking at cloud performance. And we quite like this paper, but there was a lot, because LIMPAC is a benchmark which is a synthetic benchmark, but what it does highlight is latency sensitivity, and so it does show that our code is, our systems are good. This H-series VMs that we have do work, but the Fluent I showed you really demonstrates it works on a real code, okay? And when we think about HPC in cloud, you can lift and shift and say, I'm going to put a cluster in the cloud, I'm going to put a scheduler in the cloud. That's not really the point. The point is it's on demand. And so we have something called batch, which basically allows you to wrap an application like you can see in the top right. And you can submit a job, run it, it spins up the cluster, shuts it down. A bit like what we saw earlier, but this is baked into our cloud. So you can use this for any application. And what's interesting also now is this convergence of this idea of containers, where rather than thinking of a VM and going from the operating system up and virtualizing, we can start at the application and wrap that as a container. And what's interesting is there's quite a lot of different orchestration engines, and again, we're the only cloud that actually has an open source orchestration engine that supports multiple services, including Kubernetes and DCOS and Mesosphere. And one of the things I should mention is Microsoft is actually very open now. We're actually the #1 contributor on GitHub for open source projects. So we're very much pushing everything out onto GitHub as much as we can there. And when you combine batch and you combine containers, you get this, something we call Batch Shipyard, which allows you on your laptop to create a container and run that container on your laptop, on your university machine, or in the cloud without changing the container, okay, and get InfiniBand performance with GPUs, okay. So this allows you to have that portability and reproducibility with Docker containers whilst getting the performance on the MPI. And then what's interesting, I showed you the benchmarks. We have a lot of benchmarks that show really nice scalability up to 1,000 cores. And it's Biomed, and we worked with Peter really to define this case, which is, which is NAMD. So this is what these are the standard NAMD benchmarks, okay? And this curve on the side here, which I was just plotting out, I was kind of a bit confused with it, to be honest. So basically, the curves keep getting faster, okay? And that means that it's speeding up even as we go beyond 4,000 cores to the bottom right. That's a big case, a couple of 100 million atoms, okay? The top one I showed to show you I'm not cheating. That green one is the small test case, and it flattens out at 500, okay? Because it's only a very tiny test case, as we expect. But this one shows linear scaling and I've tried to plot a scalability curve because those right-hand ones, unless you're an MD person, might not necessarily make a huge amount of that. But this shows dotted line linear scalability up to a couple thousand cores. If I plot the 4,000, the big case, the 200 million, we also get linear scalability, but the smallest job we ran was on 512 cores. The point here is we can run a job on the equivalent of half of an HPC tier 2 machine in 10 minutes with getting linear, actually here's super linear scalability. So real HPC on thousands of cores in minutes is what you can now do. And that's HPC. But in biomed, there's more to it as well. So I want to talk a little bit about genomics. So we have a team, Ravi here on the right is actually coming over. Hopefully we'll give a talk about some of the work he's been doing on SNAP, which is a new way of doing alignments that's order of magnitudes faster. So he invented that, and then what we did was we looked at some of the processing pipelines, something called BWA. How many of you know BWA GATK? Okay, so we made it go 700% faster because we've got an algorithms team, and so we're now deploying that as a cloud service, and we're doing that with our great partners, DNA Nexus, and we've actually deployed it across the Stanford kind of region with this acceleration. With that level of acceleration, we can start getting more clinical around our genomics. And when we think about things like genomics and imaging, we think about data. And data lake is a refactoring of our Bing search engine backend. So we, as one of the only companies in the world that really understands, exascale data, and we've refactored our search engine backend, and we've made it available as something called Azure Data Lake. When we see hyperscale, our single file limit is a petabyte. Okay? And then you can layer a cluster on top of that, like a Spark cluster or an R cluster. We have R server. We bought Revolution R, which does enterprise scale R. And then you can publish that as a service, queries as a service. So we've got HPC. We've got exabyte scale storage. We have encryption on that storage where you can hold the keys. Okay, so it really opens up lots of possibilities there. And when we have the data, we can apply intelligence on it. So we saw earlier some great work around CRISPR and how you can deploy functions. Well, if you have your own functions, you can deploy them through this machine learning studio, and you can basically publish machine learning as a service. And what I want to show is how that's been done to help with all sorts of different medical applications. Actually, this is CRISPR-Cas9. This is what CRISPR does. Okay, you get a guard RNA, you attach a protein, you go and you snip the DNA, and you can cut and paste DNA. But there are billions of combinations, and we saw earlier how you have to do that manual search through those things. But by applying machine learning, we can do this way, way faster. And so my colleagues in Microsoft Research have written a ranker for CRISPR called CRISPR-ML. And what they've done is they've deployed that in the cloud, so we can do on-target and off-target ranking for CRISPR. And so we can put in our input gene, and then it will run that machine learning as a service through an API to give you those results. Okay, and that's really kind of helping to apply machine learning in that case. I think I'm going to finish off talking about reproducible research. I started talking about reproducible research. We saw Jupyter Notebooks being mentioned. Jupyter Notebooks are fantastic, and typically if you go and you install it on your laptop and you have a web server locally installed, and you can do your Jupyter Notebooks, and then you might have to go and find a Jupyter Hub server somewhere. So it's a fantastic piece of technology, but there is some stuff you have to do under the hood. So what we've done is we've actually got our free service, which is Azure Notebooks. So these are free Jupyter Notebooks in the cloud. And you take your notebook file, you load it in, or you can start doing it, and they're executable. So if you have a notebook on GitHub, it will render the notebook. You can go to NBViewer and view the notebook. This runs an executable notebook for free, okay, with just a sign-in Microsoft account. Lots of people are using them. So Cambridge University is using this for their entire first-year undergraduate engineering cohort of 350 students for teaching Python. They previously had a server under the desk. They were trying to figure out how to do that. And then we came along with this. Other universities are using it. It's really, really easy to use. And so it's a really nice, again, intro, but again, it's just a free cloud service, so you can just use it whenever you like. And when we go to reproducible research, what's quite interesting is you want to share your data and your algorithms together. And so the team who made the gravitational waves discovery last year have this open science center. And what they've done is they've taken the data from that discovery and they've put it into Azure, and then they've also published then on the right their Azure their notebook, so that you can go to this Open Science Center and actually reproduce and rerun the analysis of the gravitational waves discovery last year. That is open reproducible science. And it's on the cloud on Azure, and you can do it just from a free Jupyter notebook. So it's really interesting how this sort of combination of technologies where they put the data in the cloud, we've got a hosted notebook there, and we're starting to try and enable this open and reproducible research. And you can see how the cloud gets over a lot of those barriers that you need to do that. I do want to talk about this, which is what happens when Moore's law runs out. We know that Moore's law is ending. There's a joke that is hopefully funny, that the number of people who say that Moore's law is ending doubles every 18 months. Okay, so, but it will end. And for you, using the cloud, it's not a problem. Because cloud providers say you can have an infinite amount of computing. Okay? For the people who have to provide that, it's a nightmare. Okay? So Doug Berger, who's one of the world leading experts in computer architecture, has been thinking about this for the last, actually, I think 2010 he started looking at this. And, looking at all of the different possibilities, and basically we've taken a bet on programmable hardware. So what he's holding there is an FPGA card. It's got an Intel Altera FPGA on it. And we did a test where we put those into our Bing search engine, and we ran a small test of these on about 1,600 servers, and we could double the performance of our search engine for just a 10% increase in power. Okay, and you think about that, it's really, really powerful. And we did look at GPUs. We have GPUs, so we understand that, but we've decided that the FPGAs are where we want to go. And when we deploy the FPGAs, there's lots of different ways you can do that. You can deploy them as just compute accelerators like GPUs, and that's great because you can do some acceleration. We've done something slightly differently. We've got a compute layer around the outside. We've got a network layer, and this is supposed to represent a data center, okay, where we might have a few 100,000 servers. What we've done is we've inserted the FPGAs between the servers and the network. It's actually in front of the network card, not behind it. Okay, that means that we can communicate any to any. It's called a bump in the wire, this architecture. So you put the FPGA on the wire. So we can do things like accelerated networking. So we have very low latency, called Azure Enhanced Networking, high bandwidth, low latency, but not just InfiniBand, but this is across our entire server infrastructure. And so you can do very interesting things with that. And so definitely talk to me about that if you're interested. We can give you access to some of these FPGAs. But the interesting thing is we can run across the data center with about a 10 microsecond latency. Okay. And this isn't theoretical, this is deployed. We did an experiment where we said, what can we do? We did machine translation, and we took machine translation and put it onto the FPGAs. And we could translate the whole of Wikipedia in a tenth of a second. Okay. So it was an exascale computation. It was not floating point, but it was an exascale computation that we did. And so hopefully you can see how our investments in cloud technology are really pushing the boundaries, and we're really thinking ahead around architecture for this. I want to finish off really talking about what we call research as a service. So this is the idea of making the things you're working on. In this case, Jasmine Fisher in our lab is working on executable biology. So how do we look at pathways in cells? And she's developed a tool with colleagues called Biomodel Analyzer, where you can go and you've got a cell and you can put in DNA and proteins, and you can, essentially what we're modeling is the equilibrium state. Yeah, and taking computer science technology, actually some of the technology we use to get rid of the blue screen of death, so we can actually prove that programs run to termination, okay, which causes blue screen of death as your device driver doesn't actually run, it gets into an infinite loop. Apply that computer science to biology. Because skin cells, if they don't reach equilibrium, develop melanoma, because they don't equilibrate. And there's a tool on the web that you can go to Biomodel Analyzer, and you can go and you can play with this. And so again, it shows how we can make our research available through the cloud. And some of our friends in the Netherlands have been doing something similar and been delivering research as a service in a very interesting way, and I want to let them tell you about that.
Is basically bringing together scientists in all kinds of disciplines in the life sciences with biomedical sciences. A colleague of mine met in the south of France in the workshop. We were ready to see the end of combining computer science and life sciences and decided to combine them.
I've met Dr. Watkins, which is a professor at the University of Cambridge. So he was trying to understand how different genes in blood cells interact with each other and might lead, for instance, to diseases such as leukemia. We developed the tool called Combine to try to understand how different genes can regulate each other. When we developed Combine, we were wondering whether we could apply the same technique that we use in leukemia also in animals. Therefore, we contacted Kenji, and they were excited about it.
Kenji does research to support seed breeding companies to develop new and improved crops, higher yield, better nutritional value to their crops.
We're excited to work with Nicola to see if the online tool can be applied to plant genomics. Currently, we're only looking at genes themselves. With this tool, we're also looking outside the genes. How do other parts of the genome, of the DNA, affect a certain trait? It gives us more insight into how genes work. We can provide this knowledge to plant breeders to help them make better crops.
I wanted to make this tool available for other people to use. Since the beginning, it was clear for us that Azure would provide the scalability and robustness necessary to deliver Combine as a research as a service. We created Epiton because we saw that there was not enough software engineering in life science, and we wanted to empower life scientists with innovative tools that use state-of-the-art software engineering. The challenge of this century is transforming life science in an engineering process, and to do that, you need to bring engineering into life science. And although probably I would not see the end of this journey, I would like to participate.
So it shows how he was doing his research as his PhD, and he realized he wanted to share his research. And that's why he built Combine. And on the back end, where he was in University of Amsterdam, they had a cluster. They had an HPC cluster. But it couldn't run on demand, because when you click that button, it has to spin up a bunch of machines. And that's what Azure can do. And he's actually re-implementing this with a batch system that will automatically fire up a cluster. So I've talked to you a lot about what you can do with Azure, but where do you go from here? So as part of our partnership here, if you ping me, I can give you some instructions to activate a slightly bigger than normal trial so you can play around with some of the things that you've seen. And that's quite nice just to get you going. But we also have our program of awards where we can give you larger chunks. And we're starting to work with quite a lot of people to take this real HPC where you see my benchmarks. And you can actually try it yourself and really see how this cloud HPC can work for you. There's no one solution fits all. We've built what we think is something that's very, very useful, and we want to work with you to help take you on that journey and see how you can do more epic research, as we like to say. So, thank you very much.